Hello, everybody. Thank you for being here. Welcome to Fido 101, our introduction to Fido. We are really glad that you are here. My name is Scott Bingham. I'm a product manager at Microsoft, focusing primarily on innovation and adoption of passwordless in the consumer space.
Hi, morning everyone, welcome. I'm David Turner from the Fido Alliance, and I oversee all the specification, development work, and technical activity at Fido Alliance.
So as I mentioned, I'm a product manager. I've been in products for about 10 years, but only recently I came over into the identity space. And when I first started in the identity and authentication space, it was pretty overwhelming. There are a lot of things to get up to speed on. There's a whole glossary of acronyms, new technologies and protocols to understand. And it was a lot. But what I found was that the identity and authentication community is very welcoming. And I think a big reason for that is that the problems that we're trying to solve transcend traditional boundaries. We're not trying to solve a problem for one company or a single industry. The problems that we are trying to solve are world problems. They're human problems. And as our lives and our world becomes increasingly digital, it becomes increasingly important to protect our digital identities. And all that is to say, there's a lot that goes into identity. There's a lot that goes into authentication, or identity, but authentication is really the front door. So we're really glad you're here. Hopefully this is impactful to you, and it serves as a really good primer for the passkey session, which is immediately following this. So we're going to cover some authentication basics. What is authentication? What does that actually mean? We're going to talk a little bit about the authentication landscape as it exists today, some of the problems that exist and how Fido can fill those gaps. We're going to talk about the Fido basics. We're going to go through some terms, some concepts, talk a little bit about WebAuthN, CTAP, asymmetric cryptography, really cool words. And then we're going to talk about Fido in use and at scale. So to start us off, let's talk about what authentication is. And to do this, I'm going to use an example that we're hopefully all very familiar with. The process of going through a TSA checkpoint. So you get to the airport, you have your boarding pass and your passport and your little roller wheelie bag, and you wait an hour and a half to have the privilege of talking to your friendly TSA agent. We'll call her Tessa. And there are really 3 steps to this. It's an authentication dance, sometimes called an authentication ceremony or process. Ask, act, and validate. So the first thing that Tessa is going to do in her friendly neighborhood TSA voice is say something like, "Passport and boarding pass, please." She's going to be very excited about this. That's the ask. The next part is your job. You're going to act. Big smile, you're going to hand over your passport and your boarding pass. That's the act. The next part is validate. And Tessa's very important job is to ensure that you, the person requesting access to this secure space, are actually you and should actually have access to that space. So she's going to look at your passport and ensure that the name on that passport matches your boarding pass. And then she's going to make sure the picture on the passport watches your face. You're going to pull down your mask and look like that. And then she's going to look at it a couple times, do a little funny black light thing, and if she's happy, she'll grunt, she'll give you back your things, and you'll go through and have the privilege of a cavity search. So that's ask, act, and validate. So next time you go through an airport, I want you to think about that. That is the process of authentication. There's a lot of definitions for authentication. You ask anybody in this room, you'll get 500 different answers. I like this one because I helped write it. The process of proving that the user with the digital identity who's requesting access is the rightful owner of that identity. And with good authentication, we can restrict access through systems, to networks, to applications, and to files. And there's a lot of different ways this can take place. It can be human to service. It can also be service to service. Computers need to talk to each other too. So ask, act, and validate. And while we looked at an analog real-world example, you do this 100, 200, 1,000 times a day in a digital space. Every time you pull out your phone and type in a passcode, or use Face ID, or Windows Hello, those are all ways that you authenticate digitally. Take an example of a website. You'll get a form. They're asking for your credentials. You're going to act. You're going to provide some information or a token, and that service is going to validate. Ask, act, validate. So at the dawn of computing, we needed a way to protect information. and restrict information to particular users. And we came up with this paradigm of username and password. And it's pretty basic. It is not very great. It was supposed to be, we have this bit of public information, your username, and a bit of secret information that is your password. That's supposed to be restricted to that one person. Only that person is supposed to know and have that. There's a lot of problems with this. The first is that gets overwhelming when you have 200 different digital identities to manage, and you're trying to think of passwords, unique pieces of information for all those identities, and your brain can't actually handle that. And so what do we do as humans? We kind of go to the least common denominator and we QWERTY, right? We drag our finger across the keyboard because it's easy to type, and that's going to be our password. The problem is that you're like everybody else, and everybody else is doing QWERTY too. And so we have some real fundamental problems with passwords. But they've been super successful for a lot of reasons. One, they're easy. The user experience is fantastic on these. You have a blank screen, you put 2 lines on there and a button, and someone's going to know how to access your website or your app. The other thing that makes passwords really successful is that they are surface agnostic. You can put this on a desktop, a laptop, you could put this on a microwave, and somebody is going to know how to sign in. But for all the good things about passwords, there are some really bad things about passwords, and we're going to walk through those today. Some real problems. And the first threat that we have is password spray. And we're going to use an example here that a really naughty person gets a list of usernames to a company, and what they're going to do is they're going to take those passwords that top our password list every year, our password chart every year, and they're just going to go down that username list and type in this password. And they're going to do this over and over and over again until they get a hit, and they will get a hit, and they do get hits. So they're going to go Cameron, Anita, Raj, Simone, Vivek, Terrence, and then me with my terrible QWERTY password, they're going to get in. So we have these really cool iStock photos of the hacker with the hood and the matrix code running down, reflecting their sunglasses in a dark room. That's not what they're doing. They're typing QWERTY. And if they're really good and took a computer science class in high school, they're running a script and doing this 100,000 times a second, and they're getting in. Which leads me to my favorite authentication quote: hackers don't break in, they log in. So we realized simple passwords don't work. We have to evolve. That piece of secret information that everybody is supposed to be unique to you and unique to that service, everybody's doing the same thing. So we started as an industry to educate our consumers. We said, you've got to do better. And look, these are some really cool guidelines. Have 12 characters or more. Include an uppercase and a lowercase letter. Include a number. Include a special character. No simple patterns, no previously used passwords, no part of a username, the list goes on and on. Can't be your name, your mom's name, your dog's name, your mom's dog's name, or your dog's mom's name. None of those are okay. What we'd love you to have is something like this. And people looked at that and went, probably not. And we found even that on the device that somebody is enrolling in, or the device that they're using to enter that password, will determine the strength of their password. For example, if you have a desktop with a full computer, you're much more likely to get a password like this. But if you're trying to enter a password such as this onto your laser printer, it's not going to happen. I have a laser printer in my home that I still have not connected to Wi-Fi, because to enter my incredibly complex password, you have to go through and press the down arrow. First through the A's, then the capital A's, and then the numbers, and then the special characters, and it will never happen. It drives my wife crazy, because she cannot print wirelessly, and I use USB. So people still are not doing this. And so we, as an industry, twisted their arm a little bit and said, you know what, we're going to enforce this now. So I'm sure you've seen this when you are enrolling in a new username and password the first time. There's this huge list of grayed out criteria, right? And when you type in your password and you meet that criteria, it turns a lovely shade of green, big smiley face. You feel really good about yourself. And you do that 14 more times. And if you don't do it, you get angry faces and warning messages, and you feel like a bad person. But even if you do that, we came to the realization that your password does not matter. No matter what it is, it really doesn't matter. And we're going to walk through a couple scenarios to prove that point. The first, no matter how complicated, no matter how obscure your password is, and you put it into those password checkers, right? It's like, it'll take 34 billion years to crack your password. It doesn't really matter if your password is phished. There's a lot of ways that phishing takes place. One is by email. I'm sure people in this room have received an email from a foreign dignitary asking for your bank account information to free their impoverished country. We have SMS phishing, or smishing, which is really fun to say. Someone pretending to be from your utility company, for example, saying, we'll turn off your power if you don't give us your login information. Social engineering, voice phishing, fake websites where you have a tiny error in the domain name and you come up with the screen that looks exactly like the known website it's supposed to be, and it's really just collecting usernames and passwords. So no matter what your password is, if it's phished, you're out of luck. The next, password reuse. And I know everybody in this room is guilty of this. We're going to have another example here. I work at a corporate job, and I get an email from IT that says it's been 90 days, I need to rotate my password. I say, okay. I set aside half an hour to do that in the morning. I go through each one of those criteria. I finally come up with this password, and I spend another 3 days memorizing it. So now I've got this password in my mind. And then a really cool new social media website comes out, Meta, MySpace, Facebook, which is amazing. And so I type that in there. Now I can talk to people virtually. And I say, if I can protect my virtual life with this, I can use this for my brokerage account and protect the last $14 in my 401k. And then I say, if it's okay to protect my brokerage account with this really cool password, in a moment of weakness, I visit myfreecrypto.com. Don't actually go there. I don't know if that's a real site. But I was looking for ways to supplement my 401k, and I typed in my username and password there. Unfortunately, no free crypto. They were just harvesting my username and password. So know that really bad person with the cool hoodie has my password, and they say, I'm going to try this everywhere. So they find my 401k, and they find my social media, and then they find where I work, and then in the course of a day, I have no crypto, I have no 401k, and I don't have a job. So this is the problem with password reuse. No matter what your password is, if it's compromised in one place and you're reusing it, it's compromised everywhere. And what's shocking about this is how easy it is to do. In June of 2021, the largest password compilation of all time was leaked, RockU 2021. I don't know who comes up with these names, but they're cool. 8.4 billion entries, and these keep building on each other. So another leak is going to happen, and they'll build that one on top, and it just keeps growing and growing and growing. You don't have to go to the dark web to get these. These are posted on Twitter. And these people with just a little bit of knowledge will write these scripts, and they'll run these, and they will get access to your accounts. And so we looked at the data, and we found that 99.9% of breaches happen when the user is protected by a password only. So we said, the password has failed. It is not working. It is not sufficient for what we're trying to protect. We need something else. We need a stronger signal. And so the industry came up with this concept of multi-factor authentication. You've heard this, MFA, or two-factor authentication, 2FA, or two-step verification, 2SV, TSV. It's all the same thing, all the same concept. We need more than one thing. Your password isn't good enough. You might have also heard it described as something you know, have, and are. For example, something you know, most commonly a password, but could also be the answer to a security question. What's the name of my mom's dog? It could be something you have, like an access badge, or a security key, or software token. It could be something you are, something that's intrinsic to you, such as your face, your fingerprint, heartbeat. I've seen some cool stuff with vein scanning, iris scanning. Any combination of these things provides a stronger signal than a password alone that you are who you say you are. But now, we kind of swung the pendulum. We had this really bad security, really, quite honestly, a good user experience is just typing in a username and password. It's very familiar, decades of muscle memory. But then we swung over here, where we have kind of a more complicated user experience. We have a username, we have a password. Now we have this one-time passcode thing. And it's commonly come over email or SMS or dedicated apps. And so we've complicated the user experience, which we've made a trade-off there. And I also want you to notice that the two most common ones, email and SMS, were channels that were never meant for authentication. They're meant for communication. And so we're kind of, this is a patch job. This is fixing something that's already broken or trying to. And so we have multi-factor authentication, something you are, have, and know. And we have been writing the industry to try to do this because we say, the little bit of friction is worth it because with multi-factor authentication successfully implemented, reduces compromise by 99.99%. So it's working. But that's not the whole story. MFA is clunky, phishable, and slow. So we have, you type in your password. If it's a complicated password, you've got to do that. If you're on a phone, you have to go through 3 layers of your keyboard to find those special characters. That's annoying. Then we get this one-time passcode. And if your phone's not right by your desk, if it's upstairs, you've got to go run up and grab that. Or your phone's gone. Or it's an email account, and you're on a public computer, and you've got to log in there. All sorts of problems there. It's clunky, and it's slow. You have to wait for that round-trip code. We also know that in accessibility settings, this can be really painful if you have to manage between different devices with people with low vision or people who are blind. Really not a great user experience. And it's still phishable. It's not foolproof. If your temporary one-time code is coming through email and your email is protected by a password, you're still in a phishable situation. And even with your phone number, we have SMS jacking and SMS swapping and social engineering. You calling in to pretend to be calling in behalf of your mom, and it happens all the time. So we're still not a phish-resistant or a phish-proof state. So I have this axis, this chart here. And if we're going to replace the password, if we're going to fix the fundamental underlying problem, we need to evaluate where our landscape is. And on the y-axis, we have ease of use. How easy is this to use? On the x-axis, we have security. So over in the far, far left, we have simple passwords. Easy to use. It's easy to QWERTY your password. It's not secure. Doesn't work. Then we have complicated passwords, harder to type in, marginally more secure. Then in our lower quadrant, we have increased security, but it's more difficult to use. It's clunkier. And we made that trade-off. We consciously made that trade-off. But we have this other quadrant up here. This is our opportunity section. What's easy to use and secure? The holy grail of authentication. But there's a little more to the story to that as well. And there's two other things that need to be true if we're going to replace the password. The first is interoperability. It's got to work everywhere. If I can sign in my microwave, or I can sign in on a printer, I've got to be able to sign in anywhere. So we've got to replace the password with something that works on different services, different operating systems, different platforms. The next is trustworthiness. Everybody in this room has been approached by a vendor saying, I've got a perfect solution for all your authentication needs. It's this bespoke software. It'll work. Trust us. You don't need to look at it. Just implement it. And that's not a great way to implement and deploy an authentication solution. So 4 things: usability, security, interoperability, and trustworthiness. And that's how we're going to replace the password. But those last two, interoperability and trustworthiness, are a little bit difficult to solve. And so we come up with something called standards. And what's really fun is that standards don't have a standard definition. But I like this one. A standard is a repeatable, harmonized, agreed, and documented way of doing something. So everybody, use this standard definition of a standard. So to take this out of the abstract, we're going to use another example. We're going to take the example of somebody making a smoothie, okay? So it's hot, and I've got a real hanking for a razzmatazz smoothie. So I get my blender, I put it on my blender base, I grab my frozen fruit, I put everything in there, I plug it in, I flip the switch, and magic happens, and I have my razzmatazz smoothie. But what I don't think about is all the standards that went into that process to ensure that that worked the same way every time and that I was safe doing it. I didn't worry about that blade spinning at 40,000 revolutions per minute flying off because it's secured by a bolt and a nut that have standards that dictate the threads per inch and the torque settings, right? And then when I grabbed the cable, I didn't worry about getting shocked. Because electric cable has standards about how thick the wire is, the covering on the wire. When I plugged it in, I knew it was going to fit my plug. I can make a smoothie in my bedroom, in my bathroom, in my friend's house. It's always going to work. And the electricity that came from my hydroelectric dam all the way to the power relay station, all the way to the circuit box in my house, through the walls, to the receptacle, are all standards. And so we deal with standards all the time, analog and digital. In our digital life, there are a few familiar standards: Wi-Fi, Bluetooth, USB. Can you imagine the chaos that would happen if these didn't exist? And for example, I have a laptop, and that laptop communicates via radio waves to send and receive a signal. But what if my phone did something completely different? If I had Wi-Fi and Fi-Wi, and Bluetooth and Greentooth, and Yellowtooth, or whatever it is. And you certainly couldn't make a router for that. You could have no hope of supporting all these different protocols and methods of transmitting radio waves. So we have these standards that keep us safe, and they keep us interoperable. And with that, I'm going to turn it over to David to introduce the solution that we have, a solution to completely replace passwords that is secure, easy to use, interoperable, and trustworthy.
Thanks, Scott. Hello again. So how do we get there? Fido, guess what? Guess that wasn't a secret. So Fido stands for Fast Identity Online. We've been around for about 10 years now, and we've been exclusively primarily focused on authentication and trying to make for simpler, stronger authentication. That's been our goal from day one. And I'll get into more details in a moment, but when people say FIDO 2, it generally encompassing a couple of different specification standards that will enable how the sort of the whole FIDO-based solutions work. And I'll get into that in more detail. So going back to what Scott talked about, which is your ask, act, validate, we've got a slightly different take on how that works today, because today the ask is your password, of course, the act is you type it in, validate, it takes that shared secret and it compares it to the version of the shared secrets on the server. Scott already told you why that's a really bad thing, and but that's how it works, that's the pattern. With FIDO, what we're introducing, or not introducing now, but the way FIDO works is that you still have the ask, you're prompted, you need to authenticate, but this time the act is something different. It could be touching a fingerprint sensor. It may be typing in a PIN. It could be a facial recognition. There's a lot of different gestures that may come into play to acknowledging the request to authenticate. And then there's a validation process that takes place. And in this case, and again, I'll come into a bit more detail there, but instead of using plain text, which is a password, and risky going over the wire and such, pardon me, instead, we'll be using cryptography, public key cryptography, where there is no shared secret involved, so there's nothing to phish on the line, and there's nothing stored that can be breached later on. So we have the same protocol, we have the same ceremony that people are familiar with. We've just simplified part of it, and we've made the last part much more secure. So to show you how all that works, this is sort of the visualization you normally get. Person sitting at their machine, could be their phone. They want to connect to some kind of service, relying party. And the line between the two is a straight line, nothing in between. Traditionally, you got a username, you got a password, and you go. FIDO has introduced this notion of an authenticator, which is an intermediary that manages these keys that I talked about. And what it does is it creates the key pair that you're going to use to talk to the relying party. And part of the way FIDO works is that it creates a unique key pair for every service that you connect to. So when I connect to my bank, it's my ID, that bank, and a specific key pair. When I connect to eBay, it creates a new key pair that's unique from the last one. And one of the main benefits of that is that you get the randomness, and you don't have the ability to track across sites. So it's not like you're using the same account, and there's no way for my bank and eBay to collude by saying, oh, I recognize that public key that you've given me. It's the same one over here, and I can connect them. They're all unique. Now, when the key pair is being created, this is where there's a new model that comes into play. There's a user gesture that's required. So the whole notion is we want to manage the way that those keys are created and released. And so the first step when creating it, and then when you're using it, is a user gesture is required. That it could be, again, typing in a PIN, it could be using your, whatever the screen unlock mechanism is on your phone, and that's the signal to say, okay, it's the person who's trying to connect, I'll create the keys. Once those keys have been created, it's now time to authenticate at some later point, and what happens is the service, the relying party, it creates a challenge which is sent back to the authenticator. The user, again, is prompted for the gesture, whatever is being used for doing that unlock. When they confirm the use of the private key, that private key signs the challenge and sends it back. And because the relying party already has the public key related to that, it can confirm that, yes, you sent back the same challenge, because if the challenge changes, it knows something went wrong. And it can confirm that it was signed with the same private key that was used initially on registration. So what we have is a much simpler way of doing it. Instead of typing in passwords and such, we have these very simple gestures that a user can perform. And we don't have to worry about the open text and phishability and breach aspects of passwords. So some of the basics. Here are a few of the terms that I'm going to kind of run through in the next couple of minutes, just to give you an idea of what are the different components in a whole FIDO-based authentication flow. So first, I've used the term already, relying party. I think in this audience, that's probably a fairly familiar term. It could also be called service provider. It could be corporate portal. It's whatever the thing is where you're trying to access information, your email, whatever it happens to be. So it's just the endpoint that you're trying to authenticate with. So what's the authenticator? The authenticator is that piece that I showed in the diagram earlier that creates and manages the keys for all of these different sites. And authenticators can take a couple of different forms. The more traditional one is what we call a roaming authenticator, and that tends to be a physical piece of hardware that you can carry around with you. I've got one in my wallet right now. Some have been integrated into devices like phones. Mostly, though, they're USB-based key fobs or NFC or Bluetooth. And that's a key that you can take from one machine to another and use it to log into the same site without having to enter a password. So I can log into my laptop and use the key. I can then go and log into my MacBook to the same site and use the key and never have to enter a password in either case. The roaming authenticator, the platform authenticator serves the same function, but it's what's built into the device. So it's what's built into your Windows laptop. It's what's built into your iPad or your iPhone. And it's what serves the same role as the roaming authenticator and fits into that diagram I showed. And it's the thing that creates the key, except this one's actually physically built into your device. So there's some convenience there and that you don't have to pull out a second key. Gestures, I've talked about that. That's the way in which you interact, with the authenticator itself. Again, could be a biometric interface of some sort. Sometimes it's just a touch, depending on whether you're, maybe if you're doing just using it as a second factor, which I'll talk about too. It could even be a local PIN. And asymmetric cryptography. Scott used that term. Again, this is a crowd where that term is probably a little more familiar. Given the nature of the conference, this is a key part of a lot of security systems that are out there. Just a quick recap on it, though. The first thing I want to emphasize is what we're talking about with Fido is PKI without the I. So we're using public key cryptography. We've got public-private key pairs so that the user on the end, the client, they own and maintain and manage the private keys, and then you have the server, service provider, relying party, they manage the public keys. And that's the basis of the cryptographic relationship. What Fido doesn't use, which simplifies the model, is the infrastructure part of PKI. So there's no certificate authorities involved or anything like that. So it removes a huge amount of complexity associated with trying to deploy things like Fido. And just pointing out the bottom for those who aren't hidden, who don't have heads hiding them, there's a whole list of other scenarios or other systems that people are familiar with where public key cryptography is used. So this is a well-established, well-understood form of technology for cryptographic security. So then there's the specifications. This is the standards part of things. This is where we actually wrote things down and said, here's how it needs to work. So there are two. The first is one that's called WebAuthN, and that's probably the standard you hear about the most. That was specifically developed within the W3C, and it defines the browser APIs that you need to use to do Fido. And in the simplest terms, it defined two primary interfaces. One is a create and one is a get. So it's when a relying party wants to register you, it'll call to the browser, it'll say get, send some parameters. That'll trigger the creation of the keys. Next, you come back, you want to authenticate. And again, now it says get, to get the keys that you created, and it does the challenge response that I showed earlier. The reason we need standardization here is that you can't have different ways of doing this on different platforms and different APIs. Fido just needs to work regardless of which client you're using, which operating system, which physical, whether it's a laptop or a phone. And because the relying parties, well, you're already doing this today. You know, you've got software that's designed to deal with all the variations of what these platforms do. You've got custom client code that's got to run because of the variations, say, in the operating system. One of the key benefits of WebAuthN is it's the same interface. Whether you're trying to do the authentication on an iPhone or whether you're doing it on an Android phone, you call the same WebAuthN APIs. And just as a quick mention, it's not actually just a browser thing. That's what you usually hear people talk about. But each of the platform vendors, Apple, Microsoft, Google, have also implemented at the platform level, which means if you're trying to write a native application, they've also created those WebAuthN APIs for you to use. The next one is one called CTAP. Pardon me, it's not one you're likely to hear as often because it's really down in the weeds. It's the interface that defines how those roaming authenticators, those physical security keys, talk to the platform. So again, we needed standardization. Lots of companies out there making security keys. We had to make sure that there wasn't a different bit of code necessary to talk to each vendor's key. There needed to be a consistent, well understood, and certifiable way, by the way. Fido also does certification to make sure that there's interoperability, and we do security certification as well. We need to make sure that you can use any key from any vendor. And so the CTAP specification defines how that works over Bluetooth, over NFC, and over USB. So this picture sort of shows where everything fits in. Just sort of start in the top left there. That's an example of a physical security key. It's going to use, it's the authenticator. There's going to be, signal to the gesture. In some cases, the gesture may just be touching the key. CTAP is the protocol that it uses to talk to the end user's device, whatever that happens to be. Then we have WebAuthN talking between the client and the server. And I'll point out protocol was on that list of terms you should know. You'll notice that besides CTAP, it says protocol, and WebAuthN, I'm stretching things a bit, it says protocol. It's really an API, but there's an implied protocol associated with it. The protocols are the defined handshakes, the formal definition of the programmatic ceremony that's got to take place under the hood. So it says, how does the physical device talk to the user machine? How does the user machine talk back? Similarly, how does the server talk to WebAuthN, or to the client? How does the client talk back? And then you'll notice we've got unfortunately there's a pointer on here, but these screens are so bright it doesn't show up. You've got the private key that is stored always on the client device. You've got the public key that's shared over here to, say, the relying party. If it was a roaming authenticator, the part that says CTAP in the key, that whole part would be embedded into the device itself. So I talked about roaming and platform authenticators. That would be the primary difference there. So the Fido experience, there's two models. Fido can still be used and is often still used for second factor authentication. There's a lot of scenarios where that's the right choice for a number of reasons. Sometimes it's the easiest way to integrate with existing systems. And so what you have, again, is your ask, act, and validate. And so the ask in this case is, presumably you've already entered the first thing, which is your password. You're then prompted for your second factor. You insert your security key, or just if it's there already, perhaps just touch it. And then again, you've got the validation authentication that takes place. The more common experience that you've been hearing about, and hearing about passwordless authentication and so on, is really this model. Again, you have an act, which is the prompt, and it could be on your laptop, could be on your phone, that says you need to authenticate. You do your user verification, which is your gesture. It says, yep, it's me. And then, so the ask, the act, and again, the validation. And this is the simplest model of all, and it's one where it doesn't require the use of passwords at all. So Scott already referenced these benefits of Fido. Security and ease of use were fundamental aspects of the design from the beginning. Simpler, stronger authentication has been our tagline pretty much since the beginning. And then by virtue of them being the standards, what it does is it creates an interoperable ecosystem. So it makes it easy for relying parties to be able to talk to any client that they want. It makes it easy for you to integrate with other service providers. And it creates trustworthiness. By having a consistent way of doing things, it's easier to test, it's easier to validate, and as I mentioned earlier, we can do certification. So we can certify Fido servers, we can certify the authenticators to make sure they're meeting the terms of the standards, and in some cases for the authenticators in particular, we can do security evaluations as well to make sure that they're robust enough for the level of security that a customer needs. Secure by design, unique credential with every relying party you talk to, it's phishing resistant, asymmetric key pairs, again, yay, pardon me, and standardization. Easy to use, no passwords involved in the ideal case, no one-time passwords to have to exchange, and it's just a simple gesture, not even typing on the keyboard. And I'm really quickly going to jump in and tell a story that Scott reminded me of, where you've got the email to get the one-time passcode. I was trying to log into one site, might even been through an app, and it said I needed a code. And I had to send it to an email. Well, this is something I sent up years ago to an old email account that I hadn't used in years. So I don't have it open and logged in all the time. Great. So I had to go, open the browser, log in. Oh, I need a code to log into that site. But luckily, they were able to send it as an SMS. I didn't have to go another. So I had to get 2 codes just to log into the one site. So it blew my mind that, that's sort of the worst of all things. And again, interoperability. It works in the browsers, works on the platforms, and works with pretty much all major form factors. We're not quite there yet, but when you talk, we've got a passkey presentation, which is sort of the follow-on to this, coming next and across the hall. What I expect you'll see in the future is that you can use your phone to authenticate directly to your Wi-Fi printer, and not have to type in any passwords, because it'll use the proximity of the phone to the printer as a part of the security model, and be able to use the keys that you've got. So that way you can log in, and no password is left on the device either. So even if the printer got hacked, there's no password to steal. Trustworthy, again, the benefits of standardization. No need to share credentials or share secrets. Like emails and phone numbers and so on, and typically the biometrics never leave the device, right? It's not like when I'm using a fingerprint to authenticate on my phone. That pattern for the fingerprint is never sent to the server. It's all a locally processed thing. How am I doing? A bit more time. So that leads us to what's next. Passkey. How many people here have heard the term passkey this week? There's a surprise. Okay, so everyone's heard it. Very simply, passkey is a noun, and it says a password replacement, but more accurately, it's a Fido credential. So it's that key pair, private key, public key relationship that you've already seen, but with a few extra twists associated with it. And if you want to know more details, you got to go next door. But the main benefit of it, or there's 2 main benefits. One is that those passkeys can now synchronize across devices, so that when I've registered with on my laptop, say I connect on my MacBook. Whew, there we go. Connect on my MacBook. I create a key pair. In the past, I would have had to create one on my, using the platform authenticator, the built-in one. I'd have to create one on my MacBook, and then I have to create a separate one on my iPhone. So I'd have to do 2 registrations for the same site, which clearly is a degree of inconvenience, especially when you've got lots of sites. Safe, protected, all those other things, but there's still some user challenges there. With the advent of passkey, what you're going to have is the ability for those credentials to actually sync with those devices. So once I create it on the MacBook with my bank, the next time I go to log into my bank from my iPhone, that credential will already be there, and the bank will just say, was it Face ID on the iPhone, right? To unlock the credential, and off you go. No extra registration steps required there. And what that means, the purpose of this particular slide, is that it's cross-device. So you can have a Windows machine and I don't know what kind of phone that's supposed to be. Some phone. The credentials work across those different devices, but it's all still based on the same technology, the same protected secure systems that I showed you and talked about earlier. And the second new factor that's really interesting with the use of passkeys is that I can use my iPhone, which already has the credential on it, to bootstrap a secure connection on my Windows machine. So I've registered my iPhone with the bank, I've got my key. I now want to sit down on my Windows machine, but I don't want to put the password in there. I want to connect securely. Well, I'll be able to use my iPhone to authenticate on that machine and then create a credential on that machine if I wish. So the keys, the pass keys, the Fido credentials, they're no longer bound to a single device. It's the system's being built so that they can be shared across your personal ecosystem and between your devices. And at that point, I think we have wow, I went through that quickly. Some questions? Yes? With the passkey, what happens is that the private key is the thing you own. That's your piece. It's never shared with any of the relying parties. It's the thing that gets moved from one device to another. Yes?
So, I thought you said you have to create a unique private key pair for every relying party that you log into. Is that true or not?
Yes, you create a separate. The question is clarifying, do you need to create a unique public-private key pair for every relying party? But it's every account for every relying party. So if I have 2 accounts on the same bank, I'd create 2 key pairs. So I'd have 2 Fido credentials.
How do you know that private key is unique? Can anybody else?
No, the private keys are protected. How? It depends on the implementation. They can be in hardware. Frequently, they're either hardware-based or hardware-managed in the ideal case. You can do it in software, but at that point, you're looking at, what level of security is necessary for your solution.
What's the size of the keys, the private keys? Is that a standard?
Oh, yeah. We use standard cryptography algorithms.
4096. Raw public key with a bunch of metadata.
Yeah. I never remember off the top of my head which crypto specs we're using.
I think what he's trying to ask is, what is the chance that somebody else could randomly create a private key that matches yours?
So the question is, what's the chance someone else could create the same private key? 2 parts to that. The first is, do you trust cryptography? Right? There's a fundamental question there, and this is how crypto works. We presume that you're creating large enough keys that they'll be randomized. The second part, though, is that, in fact, is a bit of an oversimplification. The pairing actually creates a larger signed thing that includes a credential ID. It contains some identifier for the user, the relying party, because part of the unphishability is that the name of the relying party is actually built into the credential, so that's how it confirms that that's how the user can't be phished, because the user's authenticator will not release the key to the wrong relying party. So in addition to the cryptographic key, there's extra metadata that's in there as well. So at the back there. Yes.
And the PIN falls under something you know.
Yes.
Less than 2 passwords, right?
So
there's a problem with that, because what we're doing is you're using the same password to protect passkeys for 100 accounts, which is, I'll say, less secure than 2-factor authentication.
So there were 2 parts. The first was about the concern about PIN being something you know. The difference between a PIN and a password, of course, is a PIN is a local thing. Right? PIN only happens or works on the device that is defining it. So I do have different PINs for different devices. Can you authenticate with an authenticator? Yes. Yes. Can you authenticate with an authenticator locally? Yes, you can. Windows Hello does that, I believe. Is that a right statement? Yeah.
Yeah, so that is really only meant as a bootstrap. And so when you complete that first bootstrap, then what's supposed to happen is that other platform will say, would you like to create a passkey for this platform? Then you create a passkey there, and then the idea is that you do that just a few times, and then no matter where you are, on any device, you've got a local platform authenticator.
So if you created the biometric on your phone first, and you log into your laptop, which has a fingerprint biometric,
Yep.
you can then just use that? Or is
Yeah.
No, not.
Wait, maybe clarify the question.
Yeah.
Sorry,
I think I understand the question. If I use, say, Touch ID on my MacBook, and well, it wouldn't go directly to Windows, so it doesn't work. Say I'm using fingerprint on my Android phone, and I got a fingerprint on my laptop. The same, the biometric is the unlocking locally. So when I unlock locally on the device, that makes the key available, say, to the Windows laptop. On the Windows laptop, it would create a new credential that'll be bound to the biometric on the laptop, which is completely separate from the biometric on the phone, because those are stored locally.
Right, okay. Still trying to get my head around how it reduces the step of having to do it each device.
I'm sorry, I didn't hear that.
So let's say you create a private key pair with all metadata on one of the devices. You want to send to the other device, one or the other, so that how does that sync mechanism work?
So the private key is only synced with devices within the same platform. It does not sync across platforms.
We'll be talking about a lot of this next door in, 5 minutes or so.
Yep.
So if
Join us at the
there's-
passkey session.
Yes.
So, couple of things, the crypto discussions, the other good thing about standards, right? It's publicly available for review.
Yes.
Historically proven that if I build my own crypto and don't publicly review it, then it could crash. Obviously, interoperability is important, but the other good thing about a standard is this is public, so everyone can review it. Crypto experts can review it.
Yep.
There's a slide about 99.99 of multi-factor authentication. I was kind of scratching my head over that slide. Is effective or better than, I mean, obviously it's better than password, but 99.99 sounds like a pretty strong statement to me. Is that?
It is a strong statement, but there's the trade-offs. There's the usability trade-offs that prevent implementation. That's the key point there.
Is the 99.99 based on something?
What do you mean?
Do you have a study that shows that or something like that?
Yeah. Yeah, we can talk after.
I actually